Hello. Imagine for me a world where facial recognition is the norm. Now imagine if you were rejected for a job because of the shape of your nose. Or a better example, the shape of your eyes caused the police to pull you over for questioning. How would you feel? Would you have a sense of injustice? Algorithmic decision-making is a privacy concern and is mentioned explicitly under GDPR. In this video, we will take a look at a famous machine learning example, the iris flower classification project, and we will see just how easy it is to defeat the algorithms. Unfortunately, bad decisions are all too readily possible. If you're sitting comfortably, let's begin. We create content around AI, ethics, data, privacy, tech, social issues and futurism. We would love to see you in a future video, so please like, share and better still, why not subscribe to our channel? There are plenty of stories where facial recognition systems have failed for certain groups of people. Algorithms try to identify features such as the position of the eyes, shape of the nose, or the form of your lips. We might not even know which facial features a system uses for matching. Similarly, they could be working to very fine tolerances. And herein lies the problem. If we have not used good quality and diverse training examples, we could actually build systems set to fail. We will come back to facial recognition once we've examined how the iris classifier can fail. The idea here is to measure certain parts of a flower and then use those measurements to predict whether your flower is a versicolor, setosa, or virginica. I have used RapidMiner, that's freely available, and you can download that from the RapidMiner website, RapidMiner Studio, and you can also download the dataset. Now I struggle to re-find the dataset, so I've included that as a resource should you wish to run this for yourselves. And now there are other tools available from Azure, Microsoft, Google and Amazon. But the thing with RapidMiner, it's easy to deploy on your laptop and you could be playing with this dataset within half an hour, I would suggest. So the whole point here is we look at the sepal and the petal. We take the width and length for each, we put those into a table. And here we have three examples. We have the widths of the sepal and petals, and we have the lengths of the sepals and petals. So we have 4 data points per flower, and the objective here is to classify the flowers into one of the 3. But first, let's discuss the basic core machine learning principles. AI and machine learning is a big area, so we're going to reduce the scope to its simplest form and look at the generalized principles to try and understand where biases and errors may occur. Now, if you're looking for using parameters for machine learning algorithms, that is completely out of scope, I'm afraid. What we're going to do now is just look at the general principles. So we start off with training data. So we begin with a blank canvas. Our machine learning algorithms know nothing about the flowers, and we produce some training data. Our first task is to prepare that data and is to label up. What we mean is, here are 4 dimensions, and that's a particular type of flower. So that's what we do for a whole bunch of data. Then we plug that training data, that labeled up data, and we put it into our machine learning algorithm so that it can learn. Once we've done this, we can get new data that the algorithm has not seen, and we can apply the trained model and then produce results. And by results, what we mean is we provide 4 pieces of information per flower, and our results will include the name of that flower. So 4 pieces of information with a classification of the flower. So fairly straightforward. And that's our generalized diagram for using machine learning. And lo and behold, if you go and use RapidMiner yourselves, you will see that our diagram matches their flow. I really would recommend our ninjas take a little bit of time out to play with some of these tools. So now let's take a look at the results to find out how our machine learning worked. Okay, we see our table. It's been populated. We have 2 extra sections. In the green area on the left-hand side, we see the classification, so how our particular flower has been classified, and then we see some probabilities or confidence levels on how accurate the algorithm thinks it was. So we take the 4 details, we generate some confidence levels, and then we've classified our flowers. Simple enough. So our first item, the sepal lengths and widths, reveal a setosa. The second is a versicolor, and the third is a virginica. What we're going to do now is throw in some test data. Now, me being me, I just want to see what happens. So instead of some real lengths, I put in some dummy sample data. So I put 1s for everything and 2s for everything, and it came back and it said these test data flowers were setosas. Okay, nothing extraordinary there. Probably fit the pattern of those flowers somehow. So I extended that again, put 3s and 4s. And then I must have crossed some threshold and I've ended up with virginica. But that's really interesting. Let me push this even further. And I started to put some crazy data in. Now these are centimeters. So plants with sepals and petals at 1 meter, I think we'll find that those flowers do not exist. However, the classification system came back and it still gave me answers. Didn't come back and say to me, Paul, you're being crazy, these don't exist. It gave me answers. And it gave probabilities of 1. Yeah, maybe that's the alarm bell. But the system did not fail. It kept on producing answers. So more graphically, what we can see is that our nice simple chart, our nice simple classification system doesn't stop. It's like a mathematical curve. It continues off into infinity. We haven't used any logic. We haven't used rule sets. We've used a mathematical projection and we've had an answer. So the key point here is, how do you make sure that your applications are working within reasonable bounds? If you rely on the AI and the machine learning, it's just going to keep giving you answers. It's not going to stop, no matter how unreasonable your requests are or your data points are. So the key point here is, how do you make sure your systems and processes are able to live within the means of AI and algorithms going beyond scope, beyond reasonable human expectations? And I would suggest this is a key area that can cause further problems. So what I want to do now is just to push our machine learning, our results, a little bit further. Okay, so let's take our data again and let's have a look. So we can see that there are some clustering. If we look at our petal length and petal width, we can see the red dots, the setosa, are clustered to one end of the chart, and then our green dots and blue dots are clustered to the upper end. If we look at sepal length versus sepal width, we still have a clear picture, but it certainly is not as clear as the first. Now, when I see something like this, it makes me think perhaps there's an opportunity to go even crazier with the test data. So I put in some minuses. My expectations were that I would influence the red dots. I would have expected the setosa to be returned in my test data. But we end up with the versicolor. So looking at the right-hand chart, the versicolor are in the middle. If I make the test data negative, my expectations are that I would influence the red dots, but actually I've influenced the green dots. I give nonsense data, and that nonsense data produces nonsense results, or rather, the nonsense data has created results that are totally unexpected for me. Herein lies the danger. If our data is somehow corrupt, unrepresentative, we can end up with horrible results. Or, to use another word, we can end up with bias. We can end up with unintended consequences. The iris example is well bounded and only considers 4 pieces of data to make a determination. There are only 3 possible outcomes for the flower type. We expect the AI systems to find patterns humans might miss in modern use cases such as cancer detection from radiography scans. Our training data consists of pictures that we have labelled as good or bad examples before submitting them to the AI system. The AI then has to determine which features must be present for a good or wrong scan. A human might not even be able to tell you why the AI went in one direction or the other. Now let's think about facial recognition systems. What if your training data contained a disproportionate number of white male sample pictures? Or, if that is too extreme for you, you might have obtained your images from an image bank built up over time. Acquiring images easily does not guarantee you a good starting point. For example, if your pictures came from social media, what about the people who do not use this medium? There could be tranches of unrepresented people. What holes could be there? How would we expect a system with a partial data set to fail? Let us now take a look at some examples. I'm sure you've all heard about the next couple of items we're going to cover. The best algorithms struggle to recognize black faces equally. We've come across this. And why is that? Is it because there was not enough data? Is it because the algorithms and the mathematical modelling just doesn't work for some reason? Equally, there are stories around how the initial facial recognition systems failed Korean people. So we've potentially got algorithms that are beginning from a point where they're biased. Let's now add ways that we might compromise our systems. So if we're using facial recognition, how about we try and compromise those systems using deepfakes? So if we're already beginning with facial recognition systems that are compromised due to their biases, and then we come across other technology that is there to defeat and fool these systems, where are we going to end up? And here's another one. Again, this is Google, but this time round it's from the other angle. We're trying to classify animals, zebras, giraffes, but when it comes to humans, the algorithms fail because humans are classified as gorillas. So here we have a second bite at the cherry for getting this completely wrong. Dangerous stuff. As we can see, if we build our systems and programs and algorithms on data that is biased initially, and our machine learning learns in certain ways, we could end up with these ridiculous stories. What are the main takeaways? First, our AI systems use mathematics and statistics to model the world. Therefore, precise boundaries for incorrect answers may not exist. We saw this one with 1 meter petals and sepals. At some point, we crossed a threshold and into impossible flowers. Consequently, testing is a considerable burden and methods must be employed to trap ridiculous results. Second, it's all about the data. We need to understand and remember that data can send us down the wrong path if there is bias or lack of representation. We need to collect data ethically. We need to ask how this data could create unintended consequences or harm. Third and finally, we need standards. We crash test cars to give them a 5-star rating if they deserve one. We're talking about benchmarking, standards, norms, and whether or not our solutions should be trusted and to what degree. What does all this mean? Well, we need to have our eyes wide open and expect problems, which is why GDPR mentions algorithmic decision-making and profiling. There is a reason why laws exist to deal with these problems. I hope you found this video helpful. Please like, share, subscribe, and I will see you in the next video. Thank you for watching.